So first of all, let me thank the organizers for inviting me and including me in this very special meeting. It's really, really great to be here. So I'm going to talk about some Ramsey theoretic statements for the real line, and in particular, we're going to look for monochromatic sumsets. And I'm in this situation where I can state the main result without any preliminaries, which I'm very happy about. So this is what I'm gonna talk about today. Consistently modulo some large cardinal, we prove the following: that if you take a finite coloring of the real line, then there is an infinite set X, so that the coloring is constant on X plus X. Okay, so no matter how you color the real line with finitely many colors, one of those color classes will contain an infinite sumset. So I would like to keep this somewhere. I'm gonna just put this on the board here too. For any finite coloring, there is an infinite X such that F is constant on X plus X. Okay, and I like to point out here that this sumset, I'm allowing repetition. So X plus X is just a set of all numbers X plus Y when X and Y both come from X. Okay, so X and Y could be equal. Okay, so in the next 30 minutes or so, I'm going to explain how this fits into the theory of partition relations, how this relates to Hindman's theorem and certain relatives, and why this statement, why your theorem is fairly optimal, in the sense that you cannot really decrease the, oops, what am I doing? You cannot really make the, sorry, what am I saying? You can't switch from R to Q or N, right? That'd be a natural thing if you could prove the same result for the rationals or the natural numbers. I'm going to show that this is not really possible. And also, you cannot change this infinite here to uncountable, right? That's another natural question, whether you can get a stronger statement. But we're going to see that that's not possible too. All right, so I'm going to say a few words about what goes into the proof of this statement. I'm not going to have enough time to explain all the details. And what I like to close this side with is that this main theorem is really a culmination of work done in the last 2 years by many people in alphabetical order: Peter Komjáth, Imre Lidl, Paul Russell, Saron, me, and Zoltán Vidnyánszky. All right. So let's see some partition relations. So we're going to start with the Pigeonhole Principle. Okay, I'm going to take this slide to familiarize you with the arrow notation too. So the Pigeonhole Principle simply says that, one version says that if you color the natural numbers with finitely many colors, then there will be an infinite set X such that your coloring is constant there. Right? One cell is infinite. So the Pigeonhole Principle is in some sense a one-dimensional statement. You're coloring the singletons, and the general Ramsey theorem is its k-dimensional analog. So instead of coloring singletons, you're coloring k-tuples, and the statement says that you will still find an infinite set X such that all the k-tuples have the same color. Right? Now, how can you generalize this theorem? Can you make the underlying set larger so that so that you can get uncountable monochromatic subsets. So a classical result says that it's not enough to go up to the continuum. So Sierpinski proved, and this is, by present standards, a simple result, that there is a coloring of pairs of the reals or pairs of the continuum with two colors, so that both colors will appear on any uncountable subset. Now, if you would like to have positive partition relations and you'd like to see uncountable monochromatic subsets, then you need to go higher. And this is what the Eldorado Theorem says. If you iterate the power set axiom enough, the power set operation enough times, you can get an uncountable monochromatic set. Right? So if you're coloring the k-tuples, you want to iterate the power set operation k minus 1 many times and then add an extra successor. And then for any finite coloring or even countably infinite coloring, you have a uncountable monochromatic set. Okay, so going back to the naturals, here's another version of the Pigeonhole Principle, which we're very much interested in now. If you color the natural numbers with finitely many colors, then there will be some infinite set X such that all the finite sums formed from that X have the same color. Okay, so the singletons, so just elements of X will have the same color, X plus Y, when X and Y are different, have the same color, and so on. Okay? In the Hindman's theorem, you don't allow any repetitions. Okay? In the negative partition relation side, I like to mention Stavo's result that extends, in some sense, Sierpinski's very, very strongly, that there are these strong colorings of pairs of Aleph1 with Aleph1 many colors, such that all the colors appear on any uncountable subset. Right? So this is a very strong witness for the failure of Ramsey on Aleph1. And finally, a positive result, Shelah showed that consistently, again, modulo some large cardinals, the continuum can satisfy a positive partition relation. Well, by Sierpinski's result, there are colorings where at least two colors appear on any uncountable subset. But that's, in some sense, as good as it gets. In this model, for any coloring with free colors, there is an uncountable set where you see at most two colors. Okay? And there's nothing special about free here. It's true that in this model, for any finite coloring, there is an uncountable set where you see at most two colors appear. Okay, so you can reduce the number of colors from any finite thing to at most two. All right. So let's look at these monochromatic sumsets for the naturals and finite coloring of the natural numbers. And let me start by a very, very simple consequence of Ramsey's theorem. So this is much weaker than Hindman's result. Okay, so let's take a finite coloring of the natural numbers. Then there is an infinite X, so that F is constant on this X circled sum X. And I just use this notation to denote this restricted sum where I don't allow any repetitions. Okay? And this is a really simple consequence of Ramsey's result. Right? If I have this finite coloring F, then I can just define a coloring of the pairs by letting the G color of X and Y be the F of X plus Y. Okay. If X is a subset such that G is constant on the pairs, then of course F is going to be constant on the restricted sum. Okay, so in the 70s, Hindman and Owings asked what happens if you allow repetitions. Okay, so is it possible that you can extend in some sense Hindman's theorem or this very simple observation to some sets which allow repetitions? So if you allow repetitions, you see two kinds of elements. You see the restricted sum where you don't have any repetitions, and you see terms of type 2x where x comes from this capital X. So by the previous statement, you can suppose that you see the same colors here, and by the pigeonhole principle, you can assume that you see the same colors here. And the question is if you can match these two constant values. Well, not always. There is a forecoloring of the naturals without infinite monochromatic sumsets. And I think this is my favorite click. This is the coloring. I think there are no typos there. So you take your natural number x, you take its base square root to logarithm, the floor, that's a natural number, and then you mod out by 4. And it's going to work. And the amazing thing, it's 4 lines. The proof is 4 lines. So suppose that we want to show that there are no infinite monochromatic sumsets. So we need to take an infinite set x and find x and y such that the color of x plus y and the color of 2x are different. So this is what I'm going to do. Infinite x, I fix a y and in x, in capital X, and then I find a small x which is much, much, much larger. Okay? How much larger? Well, I want them to be relatively close so that their logarithms differ by less than 1. The logarithm of x and the logarithm of x plus y differ by less than 1. And you can do this because the logarithm looks like this. In particular, the f values, the f of x and f of x plus y, differ by at most 1, modulo 4. Okay, so let's calculate the value of f2x. Well, the point of taking base square root to logarithm was that the times 2 in the bracket comes out as a plus 2. Okay, so the distance of f2x from fx is 2, mod 4, but the distance of f of x plus y from fx is at most 1. So they're not going to be equal. And that's it. That is why there is a forecoloring of the naturals without infinite monochromatic sumsets. It is famously open if you can do this with 2 colors. So there could be a Ramsey theory, like a Ramsey statement, which says that for any 2 coloring, there's always an infinite monochromatic sumset. You can do it with free. It's not so easy, but you can do it with free, and you can also manage that one of the color classes has density 0. So there's a very thin color class there. All right, so let's move on to R. And these investigations really, I think, started in 2015 with a paper of Hindman, Lieder, and Strauss. And they proved this very nice positive result. So if you now take a finite coloring of the real numbers, which is either bare or Lebesgue measurable, then there is a perfect non-empty x, so fairly large x, such that the coloring is constant on this sumset x plus x. Okay, so non-restricted repetitions allowed. Okay, so once you have definability, you have very large monochromatic sumsets. What about without definability? So the result is that you're not going to see uncountable sumsets, not even in the restricted case. There is, this is a result in Z of C, there is a 2 coloring of the reals so that on any uncountable sumset, you see both colors. So both colors will appear on any uncountable subset. Even you don't even need the repetitions. You can realize two colors without repetitions. Okay, so in the original paper, they proved Hindman, Leader, and Strauss. They proved this using CH, and then Peter Komjáth, and independently Bill Weiss and me, we showed this in ZFC. And we also showed that this too can't be improved to free. So you can't realize free colors without additional assumptions. All right, so when I said that in our theorem the infinite is optimal is by this result, because in ZFC there is a two coloring where two colors appear on any uncountable subset. In any case, this work was continued by Fernandez-Breton and Asaf in 2016, and they proved many nice results on how to realize more colors on sets of the form fin sum x. Again, no repetitions allowed here. And they proved some nice general theorems on uncountable commutative conciliative semigroups. Right, so these coloring results and Ramsey results are actually much more general than just looking at the real line. In any case, the strongest possible result on R you can hope for without definability is infinite sumsets and maybe allowing repetitions. Okay, right, because without repetitions, you have that very easy consequence of Ramsey, and that's already true for the naturals. Okay, so this is just the four coloring result that N has a four coloring without the monochromatic sumsets. Are there any questions before I continue? Okay. So instead of just looking at the real line, I actually want to look at this G kappa. I'm just using this notation to denote the kappa size direct sum of the rationals. So an element here is just a function from kappa to the rationals. Have a finite support, and you have a sequence from Q. You see the non-zero values. Okay. In particular, G2 to the L of 0 is just the real line. Okay, so I'm going to use this notation. I will write G kappa arrows with a plus L of 0 R if for any R coloring there is an infinite monochromatic sumset. Okay, so the same statement as before. Okay, so what's written here is that R plus L of 0 R, right? For any R coloring there is an infinite monochromatic sumset. Negation is just crossing the arrow, and then we just showed this result, right? That there is a four coloring without monochromatic sumset, infinite monochromatic sumset. Okay, so is there any chance of extending this result, this negative result, into, say, the rationals or larger direct sums? So actually this was shown by Hindman, Leader, and Strauss in the original paper, that you can also find a coloring of the rationals without infinite monochromatic sumsets. You just need to increase the number of colors somewhat. Okay, they were able to do this with 72 colors. 72 coloring of the rationals without infinite monochromatic sumsets. Well, you can take care of finite direct sums too. Finite direct sums have these 72 colorings too, without infinite monochromatic sumsets. However, something interesting happens. The only way we know how to step up this coloring is to double the number of colors. So when I want to find a coloring now of GL of 0 without infinite monochromatic sumsets, then I then it's, as far as we know, you need to double the colors. So as you're stepping up and up, you're getting this, that you can still find finite colorings, this many colors of GLFM without infinite monochromatic sumsets. And in particular, you have this corollary that if the continuum is small, then the negative relation holds for R. If the continuum is less than Aleph omega, then there is a finite coloring without infinite monochromatic sumsets. Right, so in particular, this is really going to be a consistency result. All right, so how is it possible then to get a positive partition relation? Right, how is it possible to find monochromatic sumsets? And I like to outline this idea, which is one of the crucial ingredients to our main theorem, which I just dubbed the position invariance here. Okay, so this is very simple. So elements from the direct sum look like this. You have a finite support A, and then you take a sequence of non-zero rationals and you just put it on that finite set A. Okay, that's a finite pattern. So suppose you have, say, a two coloring of this large direct sum. Now, for any pattern, you see three particular patterns here. For any pattern, you can assign a coloring of now the finite subsets of kappa by two colors. So if you take a pattern S, like this, 4, 4, you can assign a coloring of pairs by taking a finite set A, putting the pattern 4, 4 on it, and reading off the coloring from the direct sum. So these are not random patterns. If we're now using two colors, then I really want to look at these three patterns, 4, 4, 2, 2, 4, and 2, 2, 2. I don't know how many 2s I said, 2, 2, 2, 2. Now, if kappa is large enough, then there is a large, I'm going to say how large, W, so that these three colorings are constant on W. Okay, this is just by applying the Eldorado Theorem. So we have three colorings, and they're all constant, but we only have two possible choices for the constant value. So, by the Pigeonhole Principle, two of these gonna agree. And I'm gonna just look at the case when CS1 and CS2 are agree, and let's say they're both constant 0. So this is what I'm gonna do. I'm gonna construct my infinite x as follows. I'm going to take alpha beta and gamma 0, gamma 1, and so on from W, so infinitely many gammas. AI, the supports are going to be alpha beta gamma I, and I'm going to put the pattern 1, 1, 2 on alpha beta gamma I. This is exactly 1/2 S1. Right? So x0 is 1, 1, 2 on alpha beta gamma 0, x1 is 1, 1, 2 on alpha beta gamma 1, and so on. So if I collect these xi's, they're gonna form this set capital X, and they are gonna satisfy this equality. So if I want to calculate the color of 2xi, it's just gonna be the pattern 2, 2, 4. So its color is gonna be 0. And if I'm gonna take xi and xj for different I and j, you add these two patterns, 1, 1, 2, 1, 1, 2, with the alpha and beta being in the common domain. So you're going to get 2, 2, 2, 2, which is, again, has color 0. And that's it. So this shows that, elements of the form 2xi and xi plus xj has the same color. So you have your infinite monochromatic sumset. Now, in different cases where different colorings have the same constant, we might need bigger W's. So here I only use that W is infinite. In some cases, you might need that the order type of W is omega plus omega. Okay, this is just a remark that shows that this really causes some technical difficulties in the proof. In any case, you have some nice corollaries here. So this is the idea that Peter and Leader and Russell used to show that if kappa is large enough, you have these positive relations. You can always find infinite monochromatic sumset. And in particular, they showed that under GCH, even aleph omega satisfies this, already aleph omega satisfies this positive partition relation. Okay, so for any finite coloring of the aleph omega size direct sum, you find infinite monochromatic sumset. The same idea can be used to show that at least for two colorings, you're good at dimension C+. And we did this using polarized partition relations. And you can get the result for aleph omega without GCH. So with CH, but 2 to the aleph 1 being large. And we did this using a measurable and a version of Todorchevich-de polarized relations for aleph omega. So these were parts of the results that led us to this final main theorem that I like to put up again. So consistently, what we have now is that modulo and omega 1 Erdős cardinal, we have the positive relation for R2, for the real line 2. So no matter how you color the real line with finitely many colors, you can always find an infinite monochromatic sumset. And the main ingredients are this position invariance idea. I just showed you the some polarized relations which hold under MA. And the last crucial ingredient which we needed to finish the proof came from Shelah in Budapest, where we asked him about some positive relations, where this is what he said. And our answer was a face like this. And he elaborated a bit and then pointed us to this 4-paper series, which is dubbed Was Sierpinski Right, from the late 80s. And we were able to decipher this theorem. It says that consistently, modulo and omega 1 Erdős cardinal, if you have a coloring of finite subsets of the continuum with a fixed number of colors R, then you can find an uncountable set where the following happens. So the coloring is not going to be constant, but it's going to be canonical. You can find an embedding of x, an injective function from x to 2 to the omega, so that the color of a tuple only depends on the type of the finite tree that is defined by these finitely many branches. Okay? So the coloring is going to be continuous in some sense on this x in particular. I'm not defining what type of the finite tree here means, but this is the essence of the theorem. So if you put all these ideas together and work a bit, you can actually show that the real line satisfies this relation. And I like to, so yeah, this is the main part of my talk. I like to finish with a few open problems. Okay. So I like to emphasize again that this beautiful problem of O-wings is still open. So, is it possible to find a 2 coloring of the natural numbers without infinite monochromatic sumsets? Connected to our work, obviously we have a lot of questions that we're curious about. It could still be that this is a theorem of ZFC. If CH holds or the continuum is less than aleph omega, you have negative results. But it could be that for 2 colorings, you have infinite monochromatic sumset. I am the most interested in this question. It could be that aleph omega satisfies this partition relation in ZFC. And this would be stronger than our theorem. Okay, so these are some questions which are also very natural. It could be that it's enough to suppose that the continuum is real valued measurable. I was trying to show this, but couldn't push it through. I don't know if you can do the same, if you can get the same result without large cardinals. And I think this is interesting, but I haven't looked at it, whether unbalanced sumsets, whether you can get something stronger if you allow these types of things. We never optimize the number of colors. And of course, you can look at monochromatic K sumsets instead of just adding 2 sets. However, here's something funny. So in Hindman's original paper, Hindman leader Strauss paper, they showed that the finite colorings they construct, they're not going to be monochromatic on infinite K sumsets too. The funny thing is that for K at least 3, this extends to the real line. So despite the fact that we have this very strong positive relation with adding 2 sets, x plus x, there is a finite coloring of R in ZFC with no infinite monochromatic K sumsets for K at least 3. So it's not a coincidence or you know our laziness that you only see x plus x here. That's the best possible. And finally, these questions are still open from Shelah, whether you can get this positive partition relation either below the continuum or below alpha omega. And that's it. Thank you very much.